So Euler's method is the simplest method to solve our ODEs numerically. Sometimes this method, this Euler's method I'm going to talk about, is called the explicit Euler's method. And this method is based on a first order expansion, Taylor series expansion of our variable y. So y, as a function of t, is approximately equal to y0 plus the first derivative y prime, evaluated at t equals t0, times some delta t, plus 1/2 the second derivative of y, evaluated at t equals t0, times delta t squared, plus 1/6 times the third derivative of y, evaluated at t0, times delta t cubed, etc., etc., etc. So plus dot, dot, dot. I don't know why I went that far. We're going to truncate to the first derivative term, right? So if you truncate to the first derivative term and rearrange things just a little bit, what you're going to get is that y at t at t0 plus delta t is approximately equal to y at t0 plus the first derivative of y at t0 times delta t. Now sometimes we call this delta t, sometimes it's called h. I'm not sure why. It's called h. And then this first derivative of y, evaluated at t0, that's our function. That's f of t0, comma, y0. And we know what that is because we have our differential equation, right? If I'm not going to scroll back up right now, but if we had our differential equation, well, let me just write it because we're starting out with our differential equation, dy dt equals to f of t comma y, and y at t0 equals to y naught. So there we have our Taylor series expansion of y about some point t naught. But we could do our Taylor series expansion of y about any point, as long as we know the derivative there and the value of y at that point. So in general, more generally, I could write y at some point I plus 1 is equal to y, let's say at our current point I, plus h times f of ti, comma, yi. That's a little bit more generalized. So what we're looking at here is we have a new y is equal to the old y plus some slope times a time step. So this kind of makes sense, right? If I know the slope that my y is going off in, and I multiply it by my time step, then that's my step in y. So this is our Euler's method formula. So if I start out with I equals 0, or I equals 1, then I can solve for the next y. That next y then will be able to give me the y after that, and over and over and over again. So let's write this out graphically. I start out with my initial condition at t naught and y naught. With my differential equation, I can calculate the slope at t naught, comma, y naught. So when I go off in that direction, as far as my delta t will take me, so now I'm at t1, that will calculate for me my y1. Now that I have my y1, I can look at my differential equation again and calculate the next slope. Which, again, if I step forward in time, will then give me my y2. I can keep doing this on and on and on again to get my value of y3, etc. until as far as I want to go, right? So let's say I want to solve this differential equation for 400 seconds. Then I do this until I step enough times until I get to 400 seconds. And so that would kind of just generally be the approach for Euler's method. Now, there are some pitfalls to this. And so before we actually get into the numerical methods of this and actually programming this in MATLAB, there are some pitfalls to this. So the first pitfall to this is that the Euler's method is just not very good. It has errors to it, right? So you're starting off with a slope, but you're only evaluating a slope at your current point. And your slope changes. As t is changing, your slope is changing, right? And so this is just an approximation for where you're going. And it turns out this is a very bad approximation. So your error happens in your next point, but the problem is you use that next point to calculate the point after that. So errors here accumulate. What do you do about it? Well, I could make my time step really, really tiny. So every step I'm taking is really small, and so my slope approximation is good. Then errors don't accumulate very much. But I have to do a lot more calculations if I want to go integrate this problem, say, up to 400 seconds, if I have super small time steps. There are much better numerical methods to use that involve fewer calculations. The methods themselves look more complicated, but they involve fewer calculations and they're more accurate than Euler's method.